Okay, thank you. Thank you to the Science Foundation. So I would like to tell you about a somewhat different approach, but very closely related to what Ralph talked about last week and this Monday. But I want to start from the proposition project. Oh, by the way, so this comes from a project that I have been developing with two of my PhD students. I will mention the names when it comes. So, proposition. When I mention propositional logic, people automatically assume that there is nothing to say, and they fall asleep. But I want to tell you that actually this is not true. You can say a lot using propositional logic. So let me remind you of a bit of history. I don't know exactly the year, but around 1930s, logicians were interested in the following problem. So, given a first order formula phi, is there a model of phi? Decide now we know that this is undecidable, but at that time they didn't, and there were various attempts. So in fact, I mean, quite nice results. Actually, whole subjects came out of attempts to answer this question. One is, for example, Ramsey's. But I want to mention Erbrun, and that's also an excuse to advertise. So what did Erbrun do? Well, he converted, okay, he did many things, although he had very little time to dive into this now. He converted the problem of finding a model of a first order sentence to the question of finding a model for a propositional, but not sentence, but a theory. So this phi is a single sentence, and we actually get an infinite set of propositional formulas, and then we ask convert. I mean, what exactly do I mean? I will tell you. I mean, convert phi to a propositional. Yeah. What do I mean by convert? Well, you want to assign some propositional theory which is equisatisfied. So phi has a model if and only if the theory T phi as a propositional theory has a satisfying assignment. Don't really want to prove that, and it's not that relevant, but just think about it. Because why do I ask you? Because we're going to do something similar. How would you do it? Say you don't know about the proof, so how would you do it? Well, I mean, can you see?
Yes, actually.
You have. So, okay. But
after 2 weeks of Boban, we are all
You have to. Yeah. Well, you think that your model is made out of constants, so you need at least some constant, at least one. Then you want to get rid of existential quantifiers, so introduce Cohen functions, and then so this gives you lots of terms that you can build out of the constants and the Cohen functions. And then you only have universal quantifiers. I mean, you can write your formula in a form. I'm not going to do that. And then you think that your model is made out of constants. And then you can actually, if you don't care about how efficient it would be, you just plug in all the constants. So basically, the model that you're looking for will be made out of terms. Then you have to check many things. For example, you have to check that it's not going to be equational. So you have to make an equivalence relation. Two terms are equivalent. Let's see if I started proving it. I don't have to do it. Okay. But so basically, you just have to introduce lots of constants, and then if you like, you can for every formula, subformula of phi, and actually not only subformula, you have to do substitution. Substitute all possible terms, you have propositional formulas. Okay, so that's enough. Now, if you have a propositional theory T, you also know that every propositional formula can be converted to a disjunctive normal form and conjunctive normal. Now, I'm not going to do that. Okay, so we take a propositional formula F, and then we convert it to a conjunctive normal form. Okay. CNF. Now, why do I want to convert it to CNFs? Because remember, we started from a first order formula phi, then we write a theory, propositional theory T sub phi, and then which is equisatisfiable. So phi has a model given only if T, phi has a model. Now, given a single propositional formula, it's very easy to check if it has a model or not, but we have an infinite one. And that's not easy to check. But you can search for a contradiction. And the way to search for a contradiction is there are many ways, but the one I learned by teaching propositional logic is you convert your formulas into conjunctive normal forms. So it's just every formula is the conjunction of clauses, but you just think as a set of clauses. A clause is what? It's a disjunction of literals. A literal is a propositional formula or negative propositional formula. So since you have, for each formula you write finitely many clauses, but you have infinitely many formulas. So okay, you just have a bunch of clauses. And then you can search for contradiction by applying resolution. Right? So resolution is if you have one clause P, and then you have another clause non-P, then out of these two, you deduce C1 or C2. So if you have a satisfying an assignment satisfying these and these, then either P is true or false, so it satisfies these two structures. And so then you can say, okay, I start doing resolution, and my goal is to get the empty clause. If I get the empty clause, then that's contradiction, because I have to satisfy it. What does it mean to satisfy the empty clause? You have to satisfy a literal from this clause. Okay, so that is searching for contradiction. So it is, if you find the contradiction, if you can deduce the empty clause, then you know that your propositional theory is not satisfiable, and then you also know that the original first order sentence phi is not satisfied. But of course, this algorithm may not converge, may never get the empty. Okay, so this is all nice. So we want to look at infinite reversion solutions. So so you can okay. Why do I want to look at infinite propositional formulas? Well, because we want to do some analog of Edwards' theorem, but so we have not a first order sentence phi, but a sentence in infinite logic. You know, you're familiar with this logic from kappa omega. Or if you like, I don't care about that. So this is like propositional logic, but you can take arbitrary conjunctions and disjunctions, but you quantify only over finite variables. So we are interested in the following question. So the question that you would like to answer is, you're given, given phi and L kappa omega sentence. Okay, now the question of, it's not the question whether it has a model, but whether you can add a model by forcing in a certain class. When can we add a model by a nice forcing, by a forcing in the nice class? Okay. Now, of course, it's not going to be an arbitrary class. That we think of proper, semi-proper, stationary set preserving. Now, this is motivated by Ralph's theorem with David Aspero. So this. But I don't know how much you know about this. So to even start reading the paper, you have to know a lot, right? You have to know about Pmax, about determinacy, etc. So what we do is just extract, just get rid of everything, large cardinals. Well, there would be inaccessible cardinals. But just get rid of everything and go to the heart of the problem and make it kind of purely combinatorial and develop some method. Now, I would like, so I would like to cover also other constructions of poset, but we don't have, so basically I would like to have something like this. You give me a formula phi, I have an algorithm, so quote unquote, that searches for the poset in that class. And either the algorithm converges, then I get the poset, or I get, or there is no. But the problem, this we cannot do. So we can just give some examples, and I hope to convince you that what we do is quite canonical. But there are some issues why it doesn't cover all the cases, However, it does cover their case with some extra work. So if you are familiar with their theorem, you can think whether what they're doing, it can be expressed by a question given in an infinitary formula, an L kappa omega formula, find the model, and the model of this formula by a stationary set preserved. Actually, the way I stated it, it cannot be, because if you need the plus plus. I mean, there are some issues, but that would be so. I'm getting a little bit into ahead of myself, but they want to produce a P-max condition which has some iteration, blah blah blah, and this condition is in a given dense set which is universally bare. All of this you can say, but L kappa omega formulas or kappa, it's maybe quite large, but we don't care at this point. What you cannot say is that this iteration that you produce is correct about stationary sets. When you take the omega-1 iterate, then the ideal that you get is the non-stationary ideal restricted to that model, the omega-1 iterate. So it's a model size of D. This you cannot say by an L kappa omega sentence. However, you rely on density. By density, if you just do the forcing that I will describe, this will happen, and then you use the plus plus. I mean, what they prove is that n plus plus implies star, and we know that you cannot do it without plus plus. So that's where you use the plus. But I don't care. I don't want to go into so I'm just saying this so that you see that it's actually quite useful what we're trying to do. Okay, so is 5 minutes. So infinite propositional formulas. Aha. So you can similarly convert. This thing, you can write an L kappa omega sentence for them, but now I want to say that the existence of a model of phi, which is an L kappa omega sentence, can be converted to an infinitary proposition. Sort of similar to what Ed Brown was doing. That's why I didn't give you the proof of that, but I sketched Ed Brown and you just know that. So therefore, it's I will consider that this is true. Moreover, we have now what is the analog of propositional, even if they're propositional formulas, you have a bunch of propositional variables. You take and then you take arbitrary conjunctions. But it's good to record the size. Say you take, I think I call this L kappa. There is no omega, right? So you start with propositional variables and you take conjunctions, disjunctions, and negation. But conventional conjunction size less than half. um, you can sort of represent them by a tree. Could be very wide, which is well founded. But also, one more thing, you can convert your every infinitary formula to a conjunctive normal form, not maybe with the same variables. But you can add extra variables, and you say, because for example, say here you have a conjunction and then conjunction. Well, how do you do conjunction? You just introduce a variable which is equivalent to this formula, and so for each, and then you have to say, and then so for every node of the tree, the tree is consists of subformulas of your formula f, and then you have to say, well, this is a conjunction of those. So this you can say by a CNF formula, etc., etc., and of course negation and so on. So basically, by waving my hands, I consider that we have a bunch of conjunctive normal formulas, but actually every conjunctive normal form you can think of it as a set of clauses. It's a bunch of clauses, just a set of literals. And the formula says for each clause there is at least one literal that is true. So infinitely CNF formulas. So what we are looking for is a satisfying assignment, an assignment which gives for each clause at least one literal. A literal, so it's either a variable or negation or a variable, so at least one variable. And you can say many things with it. I mean, if you okay, I state that also we can describe the existence of a model of an L cup omega center, but you don't have to go through that. If you reinforcing axioms can be stated like this. Having a what do I mean by this? Let's say you give me a whole set and a bunch of dense sets, but dense sets, I think of them as maximal interchains. And then I'm asking for the existence of a filter which meets all these interchains. So for each element of P, you introduce a propositional variable which is going to be true if and only if that condition is in the field. And then you have the filter, and you have to say it's, and etc. So, okay. Now, the first thing is, what can we do? Can we do something like a resolution? And we can indeed, and that would be that will give us the answer. Sorry. So the question is, yes. So given T, maybe I should just say C, a set of clauses which are infinite, actually. When is the we want is the P in the class which has been assigned. Satisfying. Okay, so if the class K consists of all faucets, then it's basically resolution. Which is what? I like to use the language of games, which actually here you don't have to. You can just say, well, we can do infinite resolution. I mean, given two clauses, exactly the same as before. P and another clause on P, then if I have an assignment satisfying both of them, then it satisfies C1 or C2. So we can start doing this. Just whenever we have two clauses like this, we do the resolution, we have this clause, and just keep doing this. And if we are able to get the empty clause, then this is not satisfying. But the process may be transfinite, you don't know. So I rephrase this in terms of games. These are very nice games, closed games, so they're determined and we can use it. So games. The player one is the challenger, player two is the verifier. Player two claims to have a satisfying assignment, but she doesn't want to tell us. But she will answer questions, which means what kind of questions? Well, player one can play one of the clauses from our set. So this is my question. What is the question? Given this clause, which of the literals is true? So then 2 picks a literal in the clause and says, okay, I promise you this one will be true, is true in my assignment, satisfying assignment. So it's a variable. If it's a variable, then let's say this variable is true. If it's the negation, then say the variable is false. Then player one asks another question, and player two picks another, etc. And what is the goal of player one? Well, I mean, I'm player one. I want to show that you don't have, I mean, basically, I want to catch a line. In other words, I want to force you to play a literal and its negation. Then you don't have. Your assignment is not, I mean. Okay, so this is, this game last omega moves. The only requirement for player one is, for player one has no requirement, just plays clauses. Player two is required to play something that's consistent. So player two is not allowed to play a variable and its negation. That's the only thing. And if player two survives, so this is challenger. So if the verifier survives omega moves, then she wins. So the game is determined. So we know that one player has a winning strategy. And if it is player one, then this set of clauses does not have a satisfying assignment in any extension of this universe, because this, I can just, the strategy remains, I mean, the winning strategy remains a winning strategy in any well-founded outer mode. Oh, wait, did I say something wrong? It's a strategy for player two. Sorry, no, it's a strategy for player two. You just have to play. So that doesn't depend on the model it's in. Yeah, no, I think it's true.
Does it show that they verify as a strategy then there isn't some?
That's the question. So in general, since I'm not restricting the size of the clauses, if the verifier has a winning strategy, okay, let's see. When can you say that what Grigor said? We would like to say that the verifier has a winning strategy if and only if the formula has a satisfying assignment. That's our first attempt. How would you prove it? Well, there's not much you can do. You just fix the strategy for player two and let player one play all the clauses. Okay, but that works if the set of clauses is countable. That's kind of silly, right? I ask you all the questions because I don't need a total assignment. I just have to pick from each clause one literal to make it true and not run into contradiction. So that's the only thing. So if the set of clauses is countable, then player two has a winning strategy if and only if there is a satisfying. Of course, if you have a satisfying assignment, you just play it and you win. Now, what happens if the set of clauses is uncountable? You collapse them, and then you ask all the questions. But remember that the winning strategy of player two remains a winning strategy in any generic extension, because it's just finite things. So we observe that proposition two has a winning strategy if and only if C has a satisfying assignment in a generic extension. However, that generic extension is you collapse the set of clauses to be counted. You collapse the size of the set of clauses to omega. And but what we are interested in, okay, suppose you want to add a satisfying assignment, but you don't want to collapse omega 1, for example. This is kind of, we are mostly interested in proper, semi-proper stationary set preserving. And if you think about Asperger-Schindler, if I convinced you by hand waving that essentially we're looking for a satisfying assignment, the set of clauses is enormous, but we don't care. We should not even think what they are until the crucial moment. So we don't want to collapse the size of C to omega. We want to do it by, in their case, by stationary set preserving course. So this is how we get to this problem. Okay, now what are some examples that you can or cannot do? And, okay, so the project is something like this. Describe an algorithm, but this is not an algorithm in the standard sense, like a procedure. Given C, you search for a poset in, let's say, stationary set preserving poset that adds a satisfying. I want to kind of make it algorithmic. So what are some examples? Well, example, there are kind of trivial examples where you cannot do it. example 1, you can write a propositional formula describing that, saying that omega 1 is countable, or even less. I think it's actually convenient to say there is a cofinal sequence in omega 1. How can you do that? I mean, you can add lots of constants. So you take omega 1. So for each ordinal alpha, you have a constant C alpha. And you have another bunch of constants, dn. And then you want to say dn is equal to one of the C alphas. So you just say, I mean, dn is equal to alpha, so there is alpha, and it cannot be equal to two different ones. Now, you can express this by a propositional formula. There might be better ways, but anyway. And then you want to say that the dn's are cofinal. So you say for each alpha, I will have a clause saying there is n such that the alpha is less than dn. So again, what I wrote is not a propositional, but you can make it. So it's very easy to add a satisfying assignment if you allow me to collapse omega 1. But this is just expressing that omega 1 is has cofinality omega. So you can't do it by an omega 1 course. So this cannot be done. But interestingly, if you replace omega 1 by omega 2, or in any higher regular cardinal, we know that you can do it. And I would like our algorithm to actually, as a test that we have a good algorithm, it should actually produce force, and that's number force. But suppose you don't know about number forcing, you can still ask this, and there is no obvious, like here it was obvious that you cannot. But for omega 2, it's not obvious that you cannot do it. In fact, it can do it. Okay, so example 2, saying we make a 2 instead of omega 1, and the answer is yes, you can. Well, yes, you can do it by what kind of forcing? By a stationary set result. So our algorithm should actually give us number. We should reconstruct number or some version of number force. This is kind of the easiest example where something interesting. Okay, so now I want to tell you how what is the kind of approach that we take. So we can make one, we can do that. Okay, so now so we have our set of clauses. C is a set of infinite clauses. We take this whole set. This is not the whole set we will use, but this is our first attempt. This just consists of, remember, we had this game that we described. But you can do a relativized version of that game, namely, given a finite partial assignment. So if P is a if P is finite partial assignment of truth values of the positional formulas, and is not happy. And you can read the gain starting from the position P. So we describe the gain, maybe we'll just call it G of C. We started from, we started from the empty assignment, and then you play clauses, I play literals, clauses, literal, etc. But maybe we can start with a finite partial assignment. So for those variables, I already decide, and then I start playing. So if you play a clause where I already have a variable that is assigned, I just say, I give you this. Maybe I have several, I pick one. So it is an end. So this would be, I don't know if you like G sub P. If you start with P, you start with the partial assignment. So it is a finite partial assignment, and Q has a winning strategy in G P of C. So,
so just make sure GPC is a game like before, but now you have to be consistent with P.
Yeah, I have
It's
started exactly the same game as before, but I mean, you really here you don't have to use games. I mean, there is a kind of counterbending of procedure. You just have to throw away those P's for which player one has a winning strategy, and then the remaining ones, it's actually there is a larger set of finite partial assignments which has the extension property, which means if I take any member of it and you give me a clause, I can extend it to a bigger. Okay, but it's not so important. And so you just take the poset of finite partial assignments which are winning positions for 2, and the order is Q is stronger than P, if not even obviously Q stands P. So this is the poset that but this is the poset that this poset will collapse most likely if we I mean most likely it will collapse the size of clauses to be counted. So we would, and this would be our first clause, P0. And then we try to make it proper or semi-proper, etc. Now, I think we can do the proper case first, but it's kind of, they're not very different. I mean, but we don't have many applications of the proper. So I'll just do the semi-proper. And this is the approach we discussed yesterday, scaffolding. But okay, people will know that, but it's not so important because we will know. Scaffolding takes proper poset and puts models on top. So it starts with the poset and then outputs a bigger poset, which sort of has the, I mean, starts with some poset P and outputs a bigger poset S of P. P is a complete suborder of S of P, but in S of P you throw in models. And we did this yesterday for those who were here, but it was not clear what to do with it. I mean, it's just, you do it, but then what are the applications? So if you were not, was it yesterday? If you were not here yesterday, it doesn't matter because I will do it again. But now we do something similar. However, this poset P0 or H of C is not proper, semi-proper, not. And we want our scaffolding procedure to make it. I mean, so we start with P0 and we kind of make another poset P1, but that will not work either. So we have to make another poset P2 and another poset P3, etc. And we iterate this many times. Again, we have to say how many times. And at some point, we stop. And they say, basically, that will be our procedure. And either we have some models that we can put on all the time. I mean, we go up to some kappa, which will be specified. And we describe, okay, I know I'm too vague, but it will become more concrete. So good models that you can use in the next scaffolding iteration. So it's actually quite natural. Okay, so I've been waving my hands too much. So let me just try to describe you the poset P1. So what is P1? So everybody is okay with this. So what is, and okay, so we are shooting for a stationary set preserving poset. But remember, stationary set preserving means, just recall, what does it mean? I mean, it preserves stationary subsets of omega 1. But it's better to express it in terms of semi-properness. So okay, a poset Q is SSP if for every E stationary is forced by Q that E remains stationary. Okay. But I want to use a reformulation of that in terms of semi-generic conditions. So if you have a model N, elementary sum of them sum H theta, again, theta is a generic regular cardinal big enough. We never say, almost never say exactly what that, but it's something like 2 to the 2 to the size, something 2 to the size of the poset. Yeah. Okay, and then a condition Q is N comma Q. I will define directly semi-generic. Semi-generic. If I should organize the forward back. If okay, so how do we say? Well, I will give you two different. So one says that Q forces that N of G dot intersection omega 1 is N intersection. What is M of G dot? Well, you just take Q names, which are elements of N, and you interpret them as of G. This will be actually elementary sum number of G. But I want to state it in a somewhat different way. This is one, or equivalently, for every R which is less than equal Q, and for every dense set in Q, which is an element of N, there is a condition S ED which is compatible with R. So this means compatible. There is a common extension. Now, if you were defining generic instead of semi-generic, you would just require S to be in M. Here we don't, but we require that maybe S is not in the mod M, but if I put it in M and close under functions, calling functions, so this is the difference between semi-generic and generic. If Q is generic, if every R less than every 10%, there is an S in the intersection M, which is compatible with R. Semi-generic means the same, except S is not in M, may not be in M, but if you take it, if you put it in M and close under, but by the way, what is the how? I'm going to tell you, because you can say, well, we have some scaling functions, but actually you don't. Basically, what you do is you take functions in M which have S in the domain, and you just apply all. So here it's important that to note that H data satisfies the Scola principle. But I mean, this follows from ZSC, but you don't have all ZSC. You don't have the parse. So, but you have enough. So you have something. I don't want to state. Anyway, this will also be an elementary somewhat local state. You can just do the task you post. Okay, so this is what it means to be semi-generic. I mean, you know it. I would sort of use this because it's more kind of. I know it's a bit more complicated, but this is what we do. Okay, so this is semi-generic. Now, and the poset is yes. And the poset Q is M semi-proper for a single model M. If for every P in Q intersection M, there is a Q stronger than P, which is MQ semi-generic. And now the poset Q, this I'm just repeating the definition, and Q is a semi-proper poset if for all or for club many M's. But if you increase theta, it would be all M's which contain the poset, etc. The poset is M semi-proper. However, we are not looking for a semi-proper poset. We are looking for a poset that is stationary set preserving. So this is a kind of standard fact. I don't know if people know this. U is stationary set preserving if and only if it is not semi-proper for all models, but for a lot of models. There is a big set of models. If and only if the set of M's is large. It's stationary in H theta to the omega countable substance of it. Actually, more than that, it's projective station. P H theta would be omega.
This projective stationary means stationary and what?
Okay, so forget about projective. Just stationary means so any club, so it means any club. So any algebra, any function from H theta to the less than omega, there is a set like this, which is closer. Projective stationary is an extra requirement that if in addition I give you a stationary subset E subset O omega 1, you can find such M, which is closed under the algebra, but also its intersection with omega 1 is E. So again, this just means that for every F let's call this set so there are not all models are good. I mean, you have the poset is not n same proper for all, but the set of models for which it is semi-proper is very large. It's stationary and also relative to any stationary subset or omega 1 is stationary. Okay, so what do I want now? This is the definition. So now, when do we stop? Let me just give you a sketch. I thought that we also meet tomorrow. So I think it's better. These are very easy stuff, but it kind of puts you in the framework and leads you to every next step is kind of natural. So I want to tell you how you would add one more. I mean, so we have this poset. Remember we have a collection of clauses. We have the poset. By the way, if this first poset, which we call H of C, so these are finite assignment which are still player 2 has a winning strategy. So this is that. If that set is empty, that means you can't even start. That means there is no sense. That means player 1 has a winning strategy from any clause, meaning from the empty clause. Then you cannot. So the answer, in this case, the algorithm stops. You just say, okay, there is no such post. So I want to tell you how would you do the first of try to put one model on top of this post. So we have, I guess everything. We have a poset P0, which is H of C, but I will call it P0. So these are just finite partial assignments which are not lost, which are so the two can win. And now I want to say what it means. So we have our set of clauses. We have H of C, which is P0. Now we do. And we go to some theta big enough. Actually, we will have to organize things more carefully later, but let's just try to put one more. And then we take some countable elementary submodels of H theta. And then I want to say, well, what does it mean that this is, how do I define that this model is good somehow at this step? But if you remember, we had this game that was, player 1 was trying to search for contradictions. But now we want to somehow do it relative to the model n. So we do Gn of C. And the idea is that, well, somehow this assignment that we, this is countable, the assignment that you are building as player 2 should somehow respect n. I want to put that, so we make the game hard. I mean, of course, it's going to be one for each n. There is going to be a game, and which sort of says that m is okay. So actually, it should be a bit more than that. It's it should be given n and an element of because we have to start from any partial p is in p0. So we have a finite partial assignment and we have n, and now we want to say, okay, I mean, this is what we had before. We started with the empty, but then we have to actually consider GP. So now, no. May not be. Huh?
The little condition.
The little condition, a priori, there would be something, the n being good would mean something that for every p in n you can win the game. But I define it even if it's not in n. So basically, again, the idea is that the assignment should somehow respect n. And I'm going to tell you. So player 1 can, now we can do the following. So can play a clause as before, C, and then player 2 has to pick a literal in C1 and in some sense add it to P. So P is a partial assignment, and these are, we decided these are going to be on these variables we do this, and then we have another literal. Okay, this is as before, but now we allow another type of move for player 1. Player 1 can now play, remember, we have somehow to get m into play. Player 1 can play, for example, a maximal interchain in P0. Maximal interchain of density, it doesn't matter. So let's say a maximal interchain, which is in M, and maximal interchain in P0. Then what you have to do is pick a member of this interchain and add it to P. So you should pick a S0 in A0. So basically, player 2 is building a bigger and bigger partial assignment. We start with P, and then here we extended it to one literal. And here we're going to extend it, yes?
One can play either clauses or...
Yes, so there are two types of moves.
Okay.
Yeah, there are two types, and one can do either. I mean, you can or alternate it. That's not so important.
Yeah.
So do one move, then you do another type. So there are two types of moves. So player 2 can, player 1 can play a maximal interchain in P0, and then you have to choose a member of that interchain and add it to P. So basically we start with P0 equals P, and then he says P1 is P union this literal, and here is going to do P, maybe that's stage n, Pn plus 1 is going to be Pn union this S. Okay, I mean, plays at stage n, I mean. Okay, 0. I mean, this is the stage n. He plays an interchain, and then in P0, which is Sn, and then he plays this. But Okay, so first of all, this should be consistent. Is not allowed to play a contradiction. This is should be in this should be in the original poset. Otherwise, you're stuck. Okay, but this you can do because this is a maximal interchain in P0, so there is no problem. But there is the extra thing, and that is that the hull of M together with this Sn should have the same omega 1. So you are saying that, okay, so I give you a maximal interchain in P0 and I'm play one, and you have to pick one of them and merge it with P, I mean your current P. So you have some stage N, you have Pn, and then okay, I pick some member of this. But this Sn you pick, okay, the best you can do is if it is in M, then you will just, but that would be the proper version, proper in this game. Here you say, okay, maybe itself is not in M, but I can add it to M and take the hull, and I don't increase omega 1. I'm sort of shooting for semi-proper. Okay, this is a game, so now we make the game, it's relative to N. It's harder for player 2. And we say that M is a good model. I hate this name, the word good, but M is a good model if player 2 has a winning strategy for any P which is has this strategy in this game for any P which is in M. So if we start with some condition in M, but you know, your player 2 is kind of growing this finite partial assignment, and they're not going to be in M because I can ask you about a clause that's not in M, and then you have to give me an answer, meaning choose the literal from this clause and add it. Maybe that will, I mean, the new assignment may, it's only going to be like that if you think of, well, so even though we start with P's which are in M, but throughout the game, we get P's which are not in. Okay, so M is a good model at stage 0 if M is good if for every P in P0, player 2 has a winning strategy in G of N P of C. So if M is a good model, then we can use M as a side condition. We will need to show if we want this algorithm to succeed, that there will be many good ends. At least the projective station is set of good ends. Yes, and then so that's like okay. I'm going to so the poset P1 will be P0 union. So the posets are growing. You start with like just pure, these are the elements of P0 are called working parts. So they actually make decisions about the assignment that you want. And the models are the side conditions. They kind of control how the working part grow, for example. The poset P1 will consist of what should I say? Just here.
P0 with the physical models.
Yes, but so they are P1 is consist of conditions which are going to be pairs, n comma W. You see, I try to use this n is a bunch of models and W is a working part. That's actually P0. This used to be called P, but I should have called it W because P will be conditions where I have also the models. But what is N? N is a collection of models which is either empty or has one model.
One model.
At most one model. Because you see, the thing is, why it's different from the scaffolding we did before? Before we already had a poset that was proper or semi-proper, and then we just added model for no reasons, like for fun. But here we started with P0, which is not semi-proper, and we can add one model. Now say, why don't I iterate? Well, the thing is that if you can say, well, why don't I add finite chains of models already? Well, the thing is, for example, if I have two models, I should now talk about the poset P1 in the model M1. But the poset P1, and then I should actually have the move or player one should be playing, should be allowed to play maximal interchains not in P0, but in P1. But I don't have the P1. I mean, that's why you cannot add all the models at once. You have to be careful. You say, okay, this model M can be added to just a working part with no models, and I can put this one model M1. I can put it on top of that, if you can win. So the next, maybe I just tell you this and then we continue tomorrow. So basically, the next,
The omega step.
yeah, actually, but you have to go much more than steps, and there are going to be some issues of data cannot be the same because in the next stage, when you want to add one more model, so you have conditions which have either zero model, one model, or two models.
In P2, you will have anti-chains from P1 or
Yes. I will, well, okay, so first the model should be, yes, so there are going to be some issues because I cannot say, okay, I will in my hands, but tomorrow we will actually write down. It's going to be kind of natural. So you have this theta one. So the theta is going to change because in theta 0, you're taking elementary sum models of h theta 0, and this is the first step, and then you play this game. But then you have to go to a bigger theta 1, so that the poset P1 is an element. And then you should say, okay, you're taking elementary sum models of h theta 1, and you want it to be good for both poset P 0 and the poset P1. So things start getting complicated. First of all, this is an elementary sum model of h theta 1. It's not. Okay, you can say, well, if I take its intersection to h theta 0, then it's good. So I can play this game. But also, when I take, so that's one requirement. Actually, you should merge everything. So we are going to, I tell you what you have to do, and then you have to organize things so that the definitions are smooth. But okay, then you should be, if you look at the game, there should be the possibility for player one to play maximal interchains in the poset P1. And then you have to pick one member of that interchain, which maybe has a model. Less than that. And then take its working part, merge it with what you have, but then you somehow have to put that model. So so the games keep getting, well, I mean, complicated, but also the models that you put at stage alpha. So you go up to some, we'll see. I mean, kappa many steps, the models you put at stage alpha, they should be good for all previous stages and also for the stage alpha. So it's just organizing this, it takes some time. But we will see tomorrow, we don't have to do, we can just define inductive analysis.
These models always take count.
The models they count, but we have to go up to some kappa, which in our case has to be inaccessible. I don't see how to do it from this.
In the super data.
Yeah, but the thing is that the models are actually not going to be elementary submodels of H data. I mean, these are the models that we really want to use, but you see, you want this process to converge. And how do
Which
you
means end up with a semi-proper?
stationary set preserving? But you how you I mean that you have one idea how to make you have a condition and you put it in some M. Eventually, you stop after kappa base steps. Okay, you build your post. That's your P kappa. Suppose you have good models. We haven't defined it yet, but you want to say, okay, there are many models for which this poset is semi-proper. So I take some M and I take a condition, and then I would like to say, I want to kind of N semi-generic condition which extends this P. Well, what would I like to do is just put M on top and call that a condition. And if I could put M on top, that's going to be my N semi-generic condition. But this is nonsense because we have built the poset up to P kappa. We kept increasing the theta's. And then M has to have the whole poset in it. So it's going to be above kappa. So you cannot literally put M on top. You cannot literally put, you don't integrate, you take the projections. So that's what I don't want to define now. So, but the idea is to prove semi-properness for the right collection of models, you have M, which is elementary in some much bigger, H gamma, which is above everything that we have done. You cannot put an M on top, but you put some kind of whatever that means. I mean, some row on top, but we have so that's what we will do. So it's basically you increase the collection of models that you will use. Really, you care about the elementary summaries of H data, but you also want to be able to. So you go up to kappa, so you have kappa, and you take some gamma here, and you take some elementary submodel here. Then you want to put a version of that model M below. And that's not going to be an elementary submodel of some V gamma, but it's going to be an elementary and extension of a submodel. So we have to, basically, morally, you should be able to put some kind of projection of M below. And at this stage rho, we should allow these M's that come from above. Again, we don't put them all, but we put that kind of shadow of those M's. But if I could start with that definition right away and say, okay, fine, but why do you do that? And here I'm saying, I gave you the kind of intuition, and then you see that having only some models of H theta, there are some issues there. Okay, so I stop now, and then we'll do it tomorrow.